I'm recording the session, and if someone can just confirm that you can hear me, then we can get started. Okay, Ms. Leong says you can hear me, so all is well. So today, I want us to basically do what we did last week, or something similar. But in addition to that, I've set up I've set up a writing pad so that I can actually write parts of the solutions that we work through on a screen that you can see. So please be a little patient with me. It's going to require that I write quite carefully for it to be visible, for it to be clear to you. I've written on the pad before, but I've never used it for an online collaborate session. So, okay, let's get started. I have ready the slides for the first and the second week of lectures in case there are any questions that require us to go through material that we covered in the lecture. So, okay, so for now, I'm waiting for you to send me questions, or feel free to unmute your mic, ask your question, and then mute it again. So over to you. I'm waiting for you for questions. Not getting any questions yet. Okay, cool. Ms. Opperman, please can we look at question 16? And the second question, are we allowed to use calculators in the semester tests? Okay, so let me deal with the second question first, and then we'll look at the question from Ms. Opperman. Okay, so the question around calculators, to answer that in general, I or we in the department discourage the use of calculators. So as far as possible, we don't want students to use calculators. Now, this course, you'll see specifically in the questions that I posted in the tutorial for this week. There's a section, we haven't covered it in lectures yet, we'll cover it tomorrow evening. There are a number of questions that ask you to calculate a number up to a certain level of accuracy. You know, it normally says to 4 decimal places and so on. If a question says that, then you can't actually avoid using a calculator. So for those questions, you will be allowed to use a calculator. This is the first time I'm lecturing this module, and so it's actually only becoming visible to me to what extent you do need to use a calculator. So I think what I am going to do is I'm going to be explicit in setting questions for the exam and for the semester tests in terms of indicating whether you should be using a calculator or not. It's a good question. It's an important question. So to summarize, in general, no. In general, I would expect you to not use a calculator. Where it's absolutely necessary for you to calculate the answer, you will be allowed to use a calculator. In the semester test or exam, I will explicitly say use a calculator or do not use a calculator. Okay, so that answers that question. Okay, now on to the question from Ms. Opperman. I'm just going to open up the tutorial worksheet that I loaded for you so that we can see what question 16 looks like. So is that question 16 from this week's tutorial? I would guess so. I would guess so. I'm just trying to get the PDF. Just give me a few more seconds. So it's from section 11.2. Okay. Then I've opened the wrong one, so now I need to just go and get that one. Oh, okay. 11.2, number 16. Okay, I've got it. I'm going to share my screen and then we can look at it and discuss it together. Okay, so you should see the screen now and you should see question 16, A and B. So let us make it a little bit bigger so that it's more visible to you. Okay, so let's talk about this. So the first question 16a says, explain the difference between the sum from 1 to n of ai and the sum j from 1 to n of aj. So in the first expression, in the first sum, the index is given the letter I. In the second one, the index is given the letter J. So if you think about it, it really refers to the same thing. So we presumably have a sequence A1, A2, A3 up to AN. And in the first case, all they're saying is the index that numbers the elements or the points of the sequence are indexed, the index that we use is the letter I. In the second case, it's the letter J. So effectively, it's the same thing. Now, 16b is different because in 16b, we've got as the first expression, the sum I running from 1 to n of ai, and in the second expression, we've got the sum I running from 1 to n of aj. Notice that the element or the point from the sequence that we're adding doesn't have the index I, which means essentially we are taking aj, whatever it is, and adding it to itself n times. So in 16b, the second expression is simply aj plus aj plus aj n times. So every time we increase the index I, we have to write down another copy of aj. And so in the end, the sum from 1 to n of aj is simply equal to n times aj. And that's the difference between the two. And so this is, it's important that you understand the role that these indices play. Okay, I hope that's clear. Let's stop sharing and have a look at the questions that are coming in. Okay. Okay, the next one says, can you do 40 from TUT 2? 40 from tutorial 2. So that should be the same 11.2 we are looking for, question number 40. Now, for some of these, I'm not necessarily going to give you the solution. I might give you sort of an indication of how to tackle the problem. Remember, the idea behind the tutorial is that you do some work, right? The session is for discussing what you got stuck on. Okay, so let's look at 40. Now, when I look at 40, I see a number of things come to mind. The first thing that comes to mind is the fact that if I've got the sum n from 1 to infinity of an plus bn in a bracket, right? Then I've got those limit laws that became series laws, right? And those laws said, if I know that the two series converge, then I'm allowed to distribute the series symbol, that infinite sum, across the two terms inside the bracket, right? So, sorry, let's look at what the question says. It says, determine whether the series is convergent or divergent. If it is convergent, find its sum. Okay, so now I'm going to open up, I'm going to stop sharing, then I'm going to switch over and show you the notes from that lecture. Because it's important that I don't just tell you the solution, right? So, in fact, I haven't been sharing, have I? Let me share it first. Okay, so now you should see it. So there's question 40 in the top right corner of the screen. The sum n equals 1 to infinity of 3 divided by 5 to the n plus 2 divided by n. So I'll go through what I explained before, and then I'll stop sharing and switch over and show you the notes, the thing that I'm referring to. So 3 things come to mind. Firstly, the fact that when I've got a series which is actually composed of 2 other series that are added, then I'm allowed to distribute the infinite sum across the terms inside the bracket only if the 2 series inside converge. So that's the one thing. The second thing is, if I look at the first term inside the bracket, the 3 divided by 5 to the n, then that looks to me like it's going to be something that converges, right? It seems to me like it's something that will converge, because as n becomes large, the thing that I divide by is going to become a lot smaller. But we need to go back into the notes and look for theorems that confirm that. And the third thing is, if I look at the second term inside the bracket, the 2 divided by n, the sum of 2 divided by n reminds me of the harmonic series, right? And so I'm going to use one of those laws again, and I'm going to use one of those laws, and I'm going to look at the 2 as being a constant. And I'm going to multiply the 2 by the sum of 1 over n. And that's going to give me something that's related to the harmonic series. Okay, so now I'm going to stop sharing, keep the problem in mind, and I'm going to open the notes, and we see in the notes from 11.2 if we can get theorems that will support our approach to tackling this problem. Okay. I'm going to very quickly have a look at the chat series laws, but I thought we could not use them if the two series did not converge. Divergent because it could be. Okay, so Ms. Opperman, yes, you cannot use them, right? Harmonic series which diverges. You cannot use them directly. So let's go back and look at the notes. Oh, actually, let's have a look at. I also thought the same. Okay, let's look at the lecture 2 slides. I'm going to make them full screen. Right, and now we want to look at whether what we can use to help us tackle that problem. Right, so there's the start. I think we may need to go back to. Okay, so look at this example. This one should remind you of the first term inside the bracket, right? The one that says 1 divided by 5 to the n. And so the 1 divided by 5 to the n is going to be a geometric series, right? And the common ratio is going to be 1 over 5. And because the absolute value of the common ratio is less than 1, we are going to, let's go to the result for, there's the result for the geometric series, right? Here's the result. In our case, that first term, note we haven't used the limit laws yet, right? And so we can use this result. Okay, something's happening. Okay, we can't see your screen. I'm going to share the screen again. Okay, so now you should be able to see it. There. So there's the result for a geometric series. In our case, that first term, right? The 1 over 5 to the n is going to be a geometric series. The common ratio is going to be 1 divided by 5, and its absolute value is less than 1, which means we can calculate its sum, which means it's convergent. Now let's look at the second one. The second one is going to be an example of, I think number 9 is the harmonic series. So there's the harmonic series, right? So now you need to reason a little bit. You need to say, okay, so I've got the sum of two terms, an an and a bn, to make a new sequence cn. The question is the sequence 1 divided by 5 to the n plus 2 divided by n from the question. Does that result in a convergent series? And if you think about it carefully, you'll realize that it can't. If the one sequence results in a convergent series and the other sequence, the 2 over n, results in a divergent series, then the sum must be divergent. It's divergent because one of the components will grow larger and larger as n grows larger. Right. So that's how you would tackle that. I'm going to stop sharing and look at the comments again. So just to reiterate, it's important that you realize that you can't use the laws in this case because one of the series diverges. Okay, so Mr. Wu says actually 2 divided by n is the convergent. Okay, so Mr. Wu, very important thing to note here, the sequence consisting of the function that maps n to 1 divided by n, that sequence is convergent, but the series is not convergent. That's the important lesson from example 9 from that section. So go look at it again. Okay. Mr. Naika says, yes, Mr. Wu, be very careful, right? For Mr. Naika says, good day, sir. For example 11 or exercise 11 from 11.3, do we use the P series or the integral test to show that the series is convergent or divergent? Okay, so let's have a look. I'm going to open it up on that question. So this is going to be 11.3, 11. This is type 3 questions, number 11. So number 11, let me share the screen. Let me share the screen. So you should see it now. There's 11. It's the one that's in pink. It says 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. So that to me looks like something we can use the P series for, because that looks like 1, it looks like 1 divided by n cubed. So the first term will be 1 divided by 1 cubed. The second term will be 1 divided by 2 cubed plus 1 divided by 3 cubed plus 1 divided by 4 cubed, right? So that looks like it's a P series, okay? Do we use the P series or the integral test to show if the series is convergent or divergent? Okay, so let's finish off Mr. Naika's question and then look at yours. So let's look at the P series detail that we did in this lecture. I'm going to open it up and share it in the lecture for this week. Okay. Now I'm going to share. Okay, so there we go. So that's example 2 from this week's lecture. Okay, it's the last example we did before we stopped in yesterday's lecture. Okay, so now you should be able to see it. So this P series, the way we know that the P series converges or diverges is as a result of the integral test, right? So there's the detail around the integral test. And then we did example 1, we did example 2. So example 2 is the one that will give you the answer. It says, for what values of P is that series convergent? So in our case, P is going to be cubed, right? P is going to be 3 because our series cubes the denominator. And so we know from our results that when P is negative, then that limit 1 over n to the P is infinity. If P is 0, the limit is 1. In either case, we know that the limit of the sequence is not 0, and so it has to diverge, right? Because of the test for divergence. In the case where P is greater than 1, that integral, that improper integral converges, and as a result, the series will converge. So to answer your question, Mr. Nike, essentially you can use the P series test, but it is a consequence, a direct consequence of the integral test. So it's up to you how you want to write it out, because you could actually explicitly say that that infinite integral, that improper integral from 1 to infinity of 1 over x to the x cubed converges, and hence as a consequence of the integral test, the series converges as well. I hope that answers your question. Okay. Ms. Opperman, should the series be summed for 49b be similar to writing a number as a series of integers, like in example 6? Which tutorial are you referring to, Ms. Opperman? 49b. I'm wondering if it's for this week, for tutorial 2. Okay, let's have a look at the questions. Okay, so far I haven't needed to write anything. So I need to open next tutorial 2. Okay, so while you're waiting for me, I should mention that I'm on campus most days. So if you are wanting to come in to have a face-to-face session, you are more than welcome. I had one student come to see me yesterday, and it was, I think, quite nice to be able to work the way we used to work in the past. So tutorial 2. Ugh, come on. Okay, so tutorial 2, you are saying 49. Should the series be summed for 49b be similar to writing a number as a series of integers, like in example 6? Okay, should the series be summed for 49b be similar to writing a number as a series of integers in example 6? Okay, so now I'm going to open, I'm going to share, and then we can look at it together. Okay, so question 49 says, let x be equal to 0.9999 and so on, with an infinite string of nines following it. So the first question says, do you think that x is less than 1 or x is equal to 1? And then B says, sum a geometric series to find the value of x. Sum a geometric series to find the value of x. Now you compare to ask something about question 6. Calculate the first 8 terms. Does it appear that the series is convergent to divergent? Okay. I just need to look at your question again because I'm not quite sure what you mean. Be similar to writing a number as a series of integers, like in example 6. Example 6 from the lecture. Sorry, okay. So now I need to open those slides. Example 6 from, and I'm guessing lecture 2. I'm going to confirm before I share my screen. Okay, I think I understand what you're saying. I think I understand what you're saying. Now I'm going to share my screen. Actually, the way I want to do this is to take you back to maybe the first slide. I'm going to share my screen now and I'm going to answer your question. Okay, so I'm going to answer your question in a kind of indirect way. And the reason for that is this to me is a very, very nice question to test your understanding of what we are doing. So I'm going to explain something and then I'm going to go back to the comments and then I'm going to ask you a question, Ms. Opperman. So remember when we started that lecture, I started it with a slide where I showed you what we meant by repeating decimals and what we meant by this infinite expansion of decimals for the number pi. And this is what we meant. We meant pi was equal to 3 plus a tenth plus 4 divided by 100 plus 1 divided by 1,000 and so on and so on and so on. So what I wanted you to see is that last sentence on the slide now. It should be clear to you that what we are doing when adding an infinite number of terms is fundamentally different from what we do when we add a finite number of terms. So, having said that, I'm going to stop sharing the screen. Then I'm going to ask you a question, Ms. Opperman. I want you to answer by typing the answer. Right? So the first question in that 49A says, do you think this number is less than 1 or equal to 1? So I want you to answer that question first. It's equal to 1. And this is the important thing. This is the crux of this question. If you answer that it is equal to 1, then you understand something very important about the lecture. The fact, that thing that I pointed out to you a minute ago, the fact that when we take an infinite sum, we are doing something that's fundamentally different. Now we can go back to 49b and I can say to you, okay, now if you think about what you've got written there, I'm going to share the screen again because I think it's important that you see it in the context of what we've just said. That's number 49, and I think I've got the wrong. Oh, no, there we go. So x is equal to 0.9999, and so on, infinite number of nines. Now what I want you to do is look at B and ask yourself, you know what a geometric series is, right? You know it, and you can go and look up the definition. And so what I want you to do now is to look at that expression for x and express it as a geometric series. Then, once you are able to do that, now, when I say express it as a geometric series, you need to be able to give me the first term in that geometric series. In other words, the thing we've called A. Remember, a geometric series has general form A plus A times R plus A times R squared, and so on. And so in this case, I want you to go and think and write down what we mean when we say that this is a geometric series. Specifically, I want you to write down what's A and what's R. Once you've got those things, you need to determine whether this particular geometric series is convergent. And once you've determined that it's convergent, I want you to calculate the sum. So I've said too much already. I don't want to spoil your fun in solving the problems. Okay? Over to you, Ms. Opperman. And we have 5 minutes left before the break. Let's look at another question. Anyone? I haven't set up the next session yet. What we could do is to break now for 10 minutes and come back at 10:30. How's that? How does everyone feel about that? Is there anyone still there? Mr. Delwayo says, okay, cool, Ms. Opperman, great. I'm happy it's helping. Remember, the idea behind this tutorial is I'm not going to always tell you the answer, right? I want you to discover the answer. Okay, Mr. Derwayo or Ms. Derwayo, are we going to write semester tests in person? So the current information we have is that for now, everything will remain online. And we can only plan given what we know at the moment. However, I would much rather have you come and write semester tests in person. So if it does change and we as lecturers have the option, then I'm going to move for having in-person semester tests. But the current situation is everything remains online. And to be honest, my gut feel tells me that it's going to be like that for the semester. But remember, it's not up to us. We get told what to do by our bosses, by our managers and heads of department and so on. So for now, I think prepare yourself for online semester tests, similar to what you had last year. Okay. Okay, I think it's a little quiet. So I'm going to stop this session. I'm going to immediately set up a session that starts at 10:30. I'll take a quick break and then we'll meet back here in about 8 minutes or so. Malubolo, PTM Malubolo, you're going to compensate. What does that mean? I don't understand. What does that mean, Malubolo? Compensate for what? Feel free to unmute and ask your question if it's easier, as long as you mute again afterwards. Okay, we are not getting an answer from Malobolo. Okay, for you writing from home, compensate. Well, we'll compensate the way we normally do. You'll get a little bit of extra time and so on. Yes, that's the way we compensate, Mr. or Miss Malobolo, just so that you understand. The way we compensate is not up to us. I don't determine how much time you get. I get told if the students write an online semester test, then they need to be given extra yada, yada, yada. So, I am told you must have 3 versions of the exam, so students cannot easily work together. I am told you must give them an extra half an hour above and beyond the time they need for writing the test, and so on. So the answer is yes, the university or the department will compensate for that in the way that they have decided what is fair compensation. Okay, so now it's actually 10:25. Now I'm going to stop, but now I'm going to let the new session kick in 10 minutes from now. Okay.